Welcome to Module 5, Part B. We'll continue with another example of the static parameter design experiment with a bit more detailed analysis. We'll use a few more experimental design and analysis skills, which will point out some of the hazards of applying simple analysis routinely. This data is again from Minitab, so you can have a try at analyzing it yourself later if you like. The response is flight distance of a golf ball. There are 4 control factors: core material, core diameter, number of dimples, and cover thickness, all design characteristics of a golf ball. The noise variable here is the type of club, iron, or driver. I'm not much of a golfer, but in order for this problem to make sense, the clubs would have to be matched. That is, you would have to use 2 clubs that were meant to hit the ball the same distance. The analysis that Minitab suggests, and that we will replicate here, assumes that you are trying to maximize the distance traveled while minimizing the effect of the noise variable, which is the same as saying that you want to minimize the difference between the 2 clubs. This only makes sense if the clubs are matched. Here's the data. The first 4 columns are the control experiment, which just happens to be another LA, or in this case a 2 to the 4 minus 1. The noise experiment is just an L2, or a 2 to the 1, the 2 types of clubs. We're going to assume that we are hitting from the tee, and that hitting the ball farther is better. So, we're going to use the larger is better signal-to-noise metric in our analysis. In the one-step analysis, we need only to calculate the signal-to-noise metric and see which control factor combination yields the highest value. Of course, we could use the calculator in Minitab to apply the formula on the previous slide, but since Minitab has a Taguchi procedure, we'll go ahead and use that here. This is the result of using the Minitab procedure to calculate and store the signal-to-noise ratio. The procedure also allows for the storage of the mean, standard deviation, and log of the standard deviation. We will use these numbers both to evaluate our one-step analysis and in subsequent analyses. We can see from observation that the first control factor combination yields the highest signal-to-noise ratio. Note also, though, that this also has the highest standard deviation. So I guess we make all our balls with liquid cores, lower diameters, smaller numbers of dimples, and lesser thickness, right? Well, maybe. It is interesting that every other control factor combination results in a smaller standard deviation, or difference between the 2 clubs. It's interesting that the range of flight varies from an average of 20 to over 240. Do we really think that the ball variations are accounting for all the variation in flight distance? Since we don't have any true replication, which is quite common in Taguchi experiments, it is difficult to tell whether the effects we are observing are real or could be due to unaccounted for random noise. Let's apply the 2-step procedure. Here we will first maximize the signal-to-noise metric, then do our best to maximize the flight distance. Here are the effects plots for the signal-to-noise metric. It appears that all 4 variables are about equally important. So, based on these plots, we would choose thickness at high, diameter at low, dimples at low, and liquid material in order to maximize the signal-to-noise ratio. These are the effect plots for the mean. Do they look familiar? Again, we would choose thickness at high, diameter at low, dimples at low, and liquid material in order to maximize the mean. All the factors have the same effect on the mean as the signal-to-noise ratio. So the answer is relatively clear. Wait a minute. When we did the one-step analysis, we concluded that we wanted thickness at low. Other than that, the 2 analyses match. Maybe it doesn't matter that much. But the effects plots, it looked like the thickness effect was just as big as the others. Oh well, let's charge on. Maybe the modified 2-step approach will shed some light on the inconsistency. Here we will first pick the factor levels to minimize the standard deviation, then set factors to maximize the distance. These are effects plots for the standard deviation. Remember, for standard deviations we want lower values. So it looks like dimples and diameter have a larger effect on the standard deviation. Material and thickness have a smaller effect. In step 1, we'll conclude that we want dimples at high and diameter at high in order to minimize the standard deviation. Now let's see what we can do about getting a long distance. These are the effects plots for the mean distance traveled. The largest effect appears to be the diameter, with the smaller diameter ball traveling further. Second to that, the material appears to have an effect with the liquid ball traveling further. So in step 2, we'll choose the liquid material and the smaller diameter to maximize the average distance traveled. Our conclusion for the modified two-step approach is that we want dimples at high to minimize the standard deviation, and we want liquid material to maximize the mean. Unfortunately, we have a trade-off in the diameter where a higher diameter means less variance, but a lower diameter means longer distance. Mostly the three methods agree. It seems that the trade-off on the diameter becomes more clear in the modified two-step approach, though. We may still choose to have lower diameters in order to obtain longer distances, but at least we understand the trade-off we are making when we analyze the mean and standard deviation separately, as opposed to combining the two in the signal-to-noise metric. The Taguchi procedure in Minitab can fit a model, but it doesn't include all the options that some of the other design procedures have. For instance, the Taguchi procedure doesn't include a normal probability plot of the effects, something that we would find quite useful in situations where we don't have any replication. So let's take another look at the same data with the Minitab factorial procedure. Here's a normal probability plot of the signal-to-noise metric in the Goff data. Based on this plot, we can't conclude that any of the effects are significant. Here is the normal probability plot of the log of the standard deviation. The log of the standard deviation tends to be modeled better than the standard deviation. Based on this plot, we again can't conclude that any of the effects have a statistically significant effect on the variability. Same conclusion from a normal probability plot of the effects on the average flight distance. Of course, this is a relatively small number of effects to plot on a normal probability plot, but we would still expect one or two to jump out at us if something really was going on. If we assume that the only main effects are active, an assumption that is routinely made by Taguchi followers, then we might fold all the two-way and higher-order interactions into the error term and do some traditional hypothesis testing. As you can see from this output, none of the main effects are significant for the signal-to-noise metric, the log of the standard deviation, or the mean flight distance. So what's up? Does anything matter? Is it possible that there are unaccounted for sources of variation? I guess I'd like to know more about the person or the persons hitting the golf balls. I can tell you that if it were me, then there would be a lot more variation from one swing to the next than there was from one ball type to another. Taguchi analysis of experiments tend to de-emphasize replication in standard Western hypothesis testing. In this example, one which was used to demonstrate the Taguchi procedure in Minitab, illustrates the dangers of blindly applying simple analysis. Sometimes there is no substitution for knowing what you're doing.